Welcome to this video on multi-version concurrency control. If you look at concurrency control algorithms, you will see that there are basically two classes of concurrency control algorithms. One is pessimistic and the other is optimistic. So what is the difference? Well, in pessimistic concurrency control algorithms, you basically use logs to log certain rows in the database or pages or larger portions. It depends on the granularity of logging, but basically you get a log. You acquire a log that may be exclusive or shared, and then you perform certain changes in the database. So a very famous algorithm in that space is two-phase logging. Maybe you heard about that in undergrad classes or in other videos. A second class of concurrency control algorithms is optimistic concurrency control algorithms. And here the idea is you first perform changes in a protected area, and then you change the current database state. So while the transaction is running, you're not messing around with the state of the database system, but you somehow perform it in a protected area, be it local copies of the data of some sort or a different version of the database. And one algorithm in this space that is currently state of the art is called MVCC, or multi-version concurrency control. This is a very old algorithm. It was invented in the 70s already, but it is still in use in modern main memory database systems. It is basically the same algorithm as used 40 years ago, however with some optimizations, but the core idea is the same. So in this video I will explain MVCC conceptually, and I will leave away most of the implementation details you find in other explanations and videos. I will really concentrate here on the conceptual idea of the algorithm, what it is about and why it works. So let's start. MVCC, as I said already, is a variant of an optimistic concurrency control algorithm. So this is a bigger class of optimistic algorithms. MVCC is a special case of that algorithm, where the idea is that you version your database. So assume a standard table, whatever, foo, and you have a couple of attributes there, whatever, A, B, yeah, that's your table, your database table, something like that. And then you have your data there, whatever, 2, 4, C, 3, 7, D, or something like that. So that would be a standard database table. However, in multi-version concurrency control, you allow the database to keep data in different versions, much like as you would do it in a versioning system like SVN or Git, for instance. So in a version database system, there's like a hidden column of some sort that is like a from and to. So it's a time range where a certain item in the database is valid. Yeah? So you would have something like from to, which is a time interval where that, so in a version database you might have another entry with the same ID here. This would be forbidden in a standard database if this is a key. In a standard database you are only allowed to have one entry per ID. So that is what the idea of a key is about in a database system. But here you may have multiple entries, say whatever, here the value of A is 8 and B is still D, something like that. So that's a difference, but you would version it somehow in one way or the other. So this from or to could be part of the actual schema of the table, or it could be hidden. It could be a hidden schema. So you would have some sort of monotonically increasing time stamping concept. So let's say you would say from version 0 to version 1, this would be valid, and from version 2 to version whatever, maybe undefined, this would be valid. So this could be read as, okay, from the start of the database up to including version 1, this is a valid row, this is the current state of the database, but starting from version 2 up to infinity, up to now, this is the current version of the row with ID 3. So something like that. Yeah? So if you look at the different implementations, you will see that different databases do that in different ways, but the high level idea is always the same. So it's a relational database that has some table where the data in the table is versioned, and these versions can be exploited to implement multi-version concurrency control. When you look at multi-version concurrency control as any other optimistic concurrency control algorithm, it operates in 3 phases: simulation, validation, and commit. So let's look at those phases in more detail, and I will do that by using an example. Again, we have this classical example of two transactions that perform certain read and write operations. So we have transaction 1 and transaction 2. And the operations, the atomic actions, are performed in a certain order. So first we have this read operation. This reads database item A. And when transaction 2 reads this item, A is set to 5. So recall that this may refer to a certain cell in a certain table. So this is a single cell on a table. So if you have a table like that, whatever, and here you have ID, C, D, those are the attributes, right? And then you have certain rows here, 1, 2, whatever. By A, I mean I refer to a certain cell in the database. This is what I call A. Just for simplicity, this allows me to not mess around with SQL at this point in time. It makes the explanations actually way easier. So we refer to this certain cell and we track what these two transactions do with that certain cell, which of course can be referred to by using SQL. This transaction reads this cell, and when it reads it, this cell is set to 5. So we see this is 5. Then the next transaction does the same thing. It also reads the same cell. It contains the value 5. Then transaction 2 writes to that cell. It sets it to 25. That happens here. Then this transaction commits. Then transaction 1 picks up again and overwrites the same cell again. So this will be erased again and set to 15. Okay, that's basically what happens here. This is called a lost update because this value is overwritten. Yeah, it just lives for a very short period of time, then it will be overwritten directly, and that's not what we want to have. And there's a conflict of those two transactions. The problem here is that this transaction operates on an old value, and whatever it does in its application, it uses the old value to determine the new value, and that's not allowed in the database system. That's called a lost update. So everything would be fine if this transaction read 25 at this point in time. That's totally fine. So if transaction is executed completely before T2 or T2 is executed completely before T1, everything is fine. But here's a conflict. This reads an old version and then overwrites this version that was written here with its new version. We don't know what happens in between, but from the point of view of the database, this is not legal. You're not allowed to do that. So this mustn't happen in the database system. So how do we detect that? Well, in MVCC, in this first phase, we do a simulation phase. And as I said before, in the simulation phase, all these changes are just done in a protected area. So basically, all these updates are performed on local copies or different versions, but not in the current database state. So if this is written, it's not written to the database state, it's done in a different version. Then the interesting thing happens in the second phase. So eventually this transaction 2 wants to commit. And at this point in time, we have to check whether there's a conflict with any other transaction that happened concurrently. And that means now we have to check whether any data was committed by concurrently running transactions. The question we have to answer in the validation phase for transaction 2, so we're only investigating transaction 2 at this moment, is did any other transaction commit item A while T2 was running? So think about that question for a moment. Did any other transaction commit item A while T2 was running? Well, there is no commit. Yeah? Any other transaction, well, we only have transaction 1 in this case. Did this transaction commit while T2 was running? No, obviously not. The commit comes afterwards, so there was no commit. So the validation phase is pretty easy. We know there is no conflict. There was no version created in the database while T2 was running. Nothing was changed. T2 at this point in time still sees the database as of the time when T2 started. That's an easy case, so we don't have to do anything here. This means we can proceed. No other transaction committed, as I said, so we proceed to the third phase, the commit phase. In the third phase, the local version of T2 becomes the current global version. In this case, we only set the data item A to 25. So the data item in the database state is modified atomically. You actually lock the item A in the database and now change it from 5, previously it was 5 to 25. That's now done atomically in this phase, which means the changes done by T2 are brought into the database. That's it. That's the end of the third phase. And it's a relatively boring case because it's more interesting if there are conflicts. So let's continue what happens when transaction 1 now writes the data item. So here, transaction 1 continues operating. It writes database item A and sets it to 15. And the question is what happens at this point with the database state? And question B is, and what if T1 reads A again? Well, think about it. If you listened closely to what I said before, nothing happens to the database state here. This is done on a local copy, of course. Yeah, so we are still in the simulation phase in T1, so we are not allowed to change the database state, which means all these updates are performed in a protected area, as said above. Again, just to remind you, we don't mess around with the database state. That's an easy case. What happens with B, and what if T1 reads A again? So at this point in time, you could say, hey, that's fine, okay. Why would I operate on this old version of A? I could still read the most recent version. So A at this point in time in the database state is set to 25, so why not read it? Why not read this 25 again and then do this write operation? Well, this is not what MVCC is doing. The idea of MVCC is to operate on snapshots. This is also called snapshot isolation. So T1 will not read the more recent version of A as T1 operates on a snapshot of the data. So let's just look at up to this point in this text. I wrote it to the slides for you as a reference to read it again slowly. So when T1 operates, it will see all data items as of the time when it started. This is true for the simulation phase. So in the simulation phase, at this point in time, when the transaction starts, you are only allowed to read the version as of this point in time. So assume this is whatever, T42, this point in time. If anything happens afterwards in the database, due to commits, due to data that is sent to the database, T1 is not allowed to read that data. It is the same effect as if you took a picture at this point in time of the database, yeah, or a dump or a backup copy. You're only allowed to see this old version, old as of T42, but whatever happened afterwards in the database, while other transactions commit, you're not allowed to read that. So you will only see that version, whatever happens. So if you read it again, if you had another, say, read A, it would be 5. It would be the same value. No matter how often you read it, it's always the same value. And that is what snapshot isolation is about. However, note that you are allowed to fiddle around with this way of operating on the old snapshot. Many databases allow you to weaken this property. For instance, if you set the isolation level to read committed, so many database systems have so-called isolation levels. That's basically a tuning knob that allows you, it's a tuning knob, isolation levels. It's basically allowing you to trade performance with consistency, or in other words, the degree of isolation between transactions. If you want to perfectly isolate them, if you want to make sure that you're really in a serializable, fully serializable transactions, then you don't want to mess around with that knob. You want to set it to the highest possible level, which is full serializability. But if you want to trade a little bit with performance, you can weaken those properties, but you should only do that if you're really sure that you understand how that affects the consistency of the data in the database system. So that's very important. The answer to that is we don't read it again. We are in snapshot isolation mode. Yeah, then for transaction 1 comes the validation phase. And here we have to check whether this data item A was written by another transaction that committed. So again, we had this situation before, this check before. The question is, did any other transaction commit data item A while T1 was running? Well, T2 committed this item. Yeah? This item was committed here. That is the problem, and that is the conflict. That has to be detected. And why? How do we do that? Well, we make use of so-called read and write sets. In our transactions, I keep the information which keys in the database were written. This is called a write set. So you see here, nothing was written. The write set of transaction 2 is empty, but here I write to database item A, so I add it to the write set. So the write set at T2 at this point in time contains A. Yeah? And here's the same thing. The first time I write, I add something. Here, if I now wrote to B, I would add B as well, and so forth and so forth. And the check I'm performing at this point in time is to see whether the write set of the transaction I want to commit, this is the transaction I want to commit, and this is the write set of that transaction, I intersected with each and every transaction that committed while T1 was running. So in this time interval, while T1 was running, certain transactions committed. In this textbook example, this is only T2. So with each and every transaction that committed while T1 was running, I perform this write set intersection. So here I would have to intersect with each of those transactions that committed while T1 was running. Well, in this case, this is only this single write set of T2. This contains an A, this contains an A. So if I intersect the two, the intersection is non-empty, and therefore I have to abort this transaction. I have to abort this transaction. The validation phase fails. Therefore, T1 is aborted and its actions will not find its way in the database system. Yeah? So one important thing to notice, and when you Google about that, you find all these different isolation levels and guarantees the database does. One important thing to understand is that snapshot isolation, which is supported by many database systems, is slightly weaker than serializable. So serializable is this full serializability that you expect to happen if you talk about isolation. The very term, the I in ACID, you remember ACID, we had it in the previous video, the I, that is isolation. And that kind of implies, when you hear this full serializability, that is not what snapshot isolation is about. So snapshot isolation is slightly weaker, and I will show a case why that is the case. Or this class of error scenarios is called write skew anomaly. And here, the important thing to note is that we don't necessarily have a conflict between the write sets. However, we have a conflict in the sense that this transaction that wants to commit read something that was changed. So it's more a conflict of the items I read with the stuff that was written while T2 was running. So it's more or less the same case, however, not with respect to the write sets, but to the read-write sets. So before we check this case, whether that is okay, here's no conflict. You see this is writing A and this is writing B, so the intersection is empty. However, the problem here is this one. That is currently not detected. So following the explanations we had so far, this will not be detected. So that's a problem because this transaction operates on an older version. So it's similar to what we had before. This operates on A equals 5 because that is the version as of the start of T2. This was changed in between, so now the database is in the new version and you were still overriding this value B based on the old values. Okay, so how do we detect the situation? Well, we can do, as I said, we do the same write set intersection. So this write set of the transaction that wants to commit is intersected with the write set of all other transactions that committed while T2 was running. That is only this one. Well, surprise, surprise, this intersection, the set is empty. So this won't help us, but as I said, we need something else. We also additionally perform the intersection of the read set of T2, the transaction that wants to commit, with all other write sets of transactions that committed while T2 was running. So it's the same check as here. This is the same set. This is the same set, but we additionally also perform this intersection with a read set, not only the write set. And if you do that, you will see, yeah, okay, this intersection is non-empty. You see that the read set of T2 is A, and the write set of T1 is A. So the intersection of that is A, that is not empty. So this fails and we have to abort transaction 1. So by doing that, we get full serializability under the assumption that the database change operations do not add and remove rows from the database. That's an assumption that's very important here. So this only holds for update operations on certain items. As I defined it at the beginning of the video, I said, okay, we have these tables. Yeah, we have an ID, we have whatever, C and D, and then we have these cells here. And I refer to one of those cells by saying, okay, this is A. Maybe the other cell is whatever, B. Yeah, so this is basically an update operation. So if you do this these two intersections, you get full serializability with respect to these kind of update operations. However, it gets more complex if you also allow for inserting rows and deleting rows concurrently. Then we have to look at another class of problems to get full serializability. Here's a table that illustrates that a little bit. So again, what we did before was this key read, and basically we have a SQL statement like that. So we select one value from a database table, refer to it by a certain ID, as the ID is a key. We only select one column. This returns exactly one value. So one value is returned. This value A is returned. This is currently set to 5, and this is fine. You can get full serializability in MVCC if you perform these two checks. So we do this write, intersect write, and we do the read, intersect write. So this is the write set of the transaction that wants to commit. It's intersected with all write sets. So basically another way of writing that would be to say, let's erase that again. So basically the union of the write sets, of all transactions. So if that is the transaction J I want to commit, this is TJ, and that's the one I'm checking. So I have to intersect it with all of the write sets of all other transactions that committed while J was running. It's just whether they're running or not at the same time. Doesn't matter. The interesting thing is, did they commit while this transaction J was running? That's the important thing. And to do the same here with the read set, so the union over all I, so I can write an I again, here is an I, with the same thing as above. All the write sets of transactions I that are not equal to J. I have to perform this intersection. That's what I just explained. Yeah, but this is not enough for situations where you don't have where you have a non-key read. So think about this situation. You have a select count star from deals where D equals 5. So you select rows based on a certain condition. So each and every row where D equals 5. And then you count the number of rows. This is not returning a single cell from the table. This is an aggregation that's being computed. So a function on the number of rows in the database table. So let's make it more concrete. We have a table deals with 3 columns, ID, that's a key column, A and D, and we have 4 rows. So this operation will select all of the rows where D equals 5. Well, surprise, that's this one, right? This one and this one. And then it will count the number of those rows. So we would expect that 2 is returned. Yeah, that is what happens. 2 is returned because this row qualifies, count star over that is 2. So now the second transaction, transaction 2, performs an update to the table. It says, okay, in that table deals where the ID equals 4, that's this one, ID equals 4, I want to set D to 5. Yeah, this value will be set to 5. Here we see it marked here. Okay, now we have 3 rows where D equals 5. And of course, if I execute this again, what happens? Think about it for a moment at multi-version concurrency control. What happens at this point in time? Assume T1 executes this query again. Now the table has 3 rows where D equals 5. Well, the answer is, of course, we get the same result. It must be the same result. Why? Because we operate on a snapshot. T1 sees a version of the database as of the time when T1 started. So we cannot get a different version. No problem. Yeah? So you would wonder, Yeah, so why is that a problem? Yeah, we will see in a moment, but for the moment, during the simulation phase, we get the same result. It's no problem here. T1 also performs an update, so it sets the cell as before in the previous examples. It sets this cell in the table to C, previously it was B, now it's C. What T1 reads has an influence on the database. That's very important. If it were only reading, it doesn't matter. There's no problem whatsoever, but it performs an update. It changes the state of the database. And the problem here is that we don't really know how this update statement was influenced by these other read operations. That's something we don't see from the point of view of the database system. That is hidden in the application code, and we don't have access to that. So now transaction 1 commits. Well, the interesting question is what happens at this point in time. So we want to commit. This means we have to enter the validation phase. So in the validation phase, if we now checked, if we ran this query again, we would receive a result of 3. This is the state of the database as committed by T2. So if we run this query, 3 should be returned. The problem here is that from what we learned so far, we won't see that problem. We don't see it because, as I told you before, we will intersect read and write set. So the stuff we do is there's the write set intersection or something like that. So what is the write set of T1? Well, T1 only changed a single cell, that's this one, that was changed to C eventually, that's the write set. And the write set of T2, well, what is that? That's this one. That's the only value that was changed by T2. This was changed from 4 to 5. So if I intersect those two, well, this key and this key, it's empty. So it's fine, no problem with respect to write set intersection. Then we do the read set versus write set intersection. Write set is the same. But what is the read set of T1? Well, that depends on how you define that. So what you see is here, basically this row was read by T1 during this statement, and that row was selected by T1 during that statement. So again, with respect to read set and write set intersection, that's an empty set. The intersection is empty, so MVCC would proceed to say, hey, it's all fine, everything's fine. There's nothing in those intersections, so I could commit the transaction. But that's not true. That's not true because here we're operating on the old value. It's a similar situation as before, but we're operating on an old database state that was computed as a function of database cells. So what I'm doing is here, I compute the count over those two rows, but actually here, in the validation phase, if I executed this query again, I would receive 3 rows. Those 3 rows would be selected. So that's a different state. So the database has moved on. If you look at that, you will see the problem is a where clause, of course. So think about it for a while. You see, okay, the rows that are considered in this query, the rows that are the input to this computation are done based on a where clause on the selection. I say, okay, the rows where d equals 5. However, the result just of this statement will change if I change one of the rows to d equals 5. Here, add another row that qualifies basically. So if I execute this again here, this will return 3 rows. So the problem is that on a very high level, you have 2 queries here. So this is query 1 executed at T1, and this is query 1 executed at T2. So what I want to make sure that is that query 1 executed at T1 returns the same result as query 1 executed at T2 or any other point in time while the transaction is running. So if that appeared again, I want to make sure that it always returns the same result. So the thing I could do here in the validation phase is to rerun those queries, get this result set, get that result set. If there's any difference, you immediately abort the transaction. Of course, the problem with that is that you would have to rerun the query, and those queries are potentially expensive. So a cheaper way, implementation-wise, to fix that is to say, okay, I don't run the entire query, but I just rerun the where clause. So you could say, I run the where clause against the version as of T1. So you say just the where clause as of T1 and check whether that is the where clause of T2, whether that returns the same result. If that is the case, you're fine to commit, and then you detect these kind of phantoms. So that's something you need to consider in implementing MVCC. If you also want to avoid phantoms, you have to also investigate this problem. You have to make sure in the implementation that you don't run into this trap that concurrent insert and delete operations or changes to the database that change the result sets returned. Yeah? So in this situation, you might say, okay, here I don't have a where clause, so there's no problem. You don't have a phantom problem because the number of rows here doesn't depend on a particular item in the database. Yeah? So it doesn't depend on the value of D. So it will always return 4. This will return 4 because we have 4 rows. And here, when you execute it again, you again have 4 rows. Yeah? That will return 4, and that will return 4. However, you still get the same problem if concurrently you don't have an update but an insert. If you assume you insert something, you don't update but you insert some row into the database table, and then you would have 5 rows. Here you would have 4, you insert something, then you would have 5 rows. You run into the same problem. So this is the same kind of problem that occurs. It's still a phantom problem. And you basically wouldn't have a where clause, so this check wouldn't make sense anymore. You could still perform the check on the query level, so this query result would differ from the query result executed at a later point in time. That would be one way of doing that, of course. Or if you want to perform it on the where level, which doesn't make a big difference at this point, you say where true. Yeah? You would say, it sounds a little bit stupid, but would help to fix your algorithm. You say where true at T1 equals where true at T2. Yeah? And then you have basically, you can leave away the where clause. This doesn't make a difference, but basically implicitly that is what it means. Yeah? Select count star from deals where true, and that will return a different result. If you only look at where true, this will compute 4 rows at T1. If you execute again at T2, it will compute 5 rows, so you get a different result, and therefore you should abort the transaction. Yeah, that is a phantom problem, and that's important to note. Yeah, one note about main memory databases. So modern databases are based on main memory. Often all of the data fits into main memory. We are currently seeing a revival of MVCC in main memory database systems. You can make it even better than MVCC. I will link to a paper we published at SIGMOD 2018. It's one of the best database conferences internationally. I will put a link to the paper down there. There we will explain how you can get even better than MVCC. In particular, if you want to mix OLTP and OLAP in the same transaction, like in real-time data warehousing, we have a better solution for that. So check out our paper. We compare against MVCC there and explain how you can get even better. One thing to note that's really important is if you are considering implementing concurrency control, well, think twice about it, because do you really need it? So you really need to understand whether you need concurrency control at all. If you think about the amount of work done by a transaction, that's typically way less than a millisecond. So less than a millisecond to execute a single transaction in the modern memory system. Well, and if you can afford to run them in serial, this means you can get at least 1,000 transactions per second if run in serial mode, at least. Yeah? So depending on the use case, maybe that already fixes the problem. Then the simple solution to implementing concurrency control is to say, well, I just don't allow for concurrency control. I just run all my transactions in serial mode and I'm happy with that. So you save the overhead of implementing concurrency control. Yeah? Often that is a very fine solution, and that was advocated in systems like HStore that does exactly that. However, there are situations where you really want to have concurrency control. And the important situations where that is the case is if your user interface is programmed in a way that, I mean, you have this interface, you have a mask in your, here's your buttons, whatever, yeah? And then you have, here's a field where you enter data, maybe name and whatever, salary, something like that. So you enter stuff here. And how that is programmed is once you open this user interface, you send a begin transaction to the database. And then whenever you change something, you change the update info to the database system. And only when you say save, yeah, that triggers a commit. So basically, depending on how long the user takes to enter the stuff, the transaction will be kept open. In this kind of situation, you don't want to run your transactions in serial mode. That doesn't make any sense. You really have to make sure that you have concurrency control. That's one way one situation to consider. Of course, you could also rewrite this kind of interaction to make sure that only at the end the transaction is sent to the database system. That's another story that would fix that problem. But if you have applications that do that, you have to live with it. The other is long-running queries. So in particular, if you mix OLAP with OLTP, so OLAP again, those are analytical queries as executed in a data warehouse, for instance, and they may run long time, seconds to minutes. Well, and if you run in serial mode, so any OLAP transaction would block the entire database system. Doesn't make any sense. So you have OLAP is typically on the order of seconds to minutes. Those, if you think about execution time, OLTP is whatever nanoseconds to nanoseconds. I mean, let's not exaggerate. It's like a microsecond to millisecond range. So that's a huge difference here. And if you want to run those analytical queries that touch large portions of the database together with these OLTP transactions, then yeah, this is called a mixed OLTP and OLAP, or real-time warehousing. Real-time warehousing. Then you really want to make sure that you implement concurrency control. Again, as alluded to before, there are better solutions than MVCC. Check out our paper. There's a link in the description of this video. And there we explain how that works. Okay, that's it about MVCC. So again, keep in mind, there are multiple checks you have to perform. Basically, it boils down to performing these sets of write set versus write set. The transaction that wants to commit the write set is intersected with the write set of transactions that committed while T1 was running. And this may be any other transaction running concurrently that committed. Yeah, here it's only one. In order to avoid write skew, we also have to intersect the read set of the transaction that wants to commit T1 with the write sets. And additionally, if you want to avoid the phantom problem, you have to do even more. You have to check whether the results of the individual statements issued by the transaction return the same result as of the time when the transaction started and when it ended. Yeah, thanks for your attendance. I hope this video was helpful. I would be happy if it was helpful that you hit like or subscribe to my channel. I will follow up with more videos on database stuff. If you have any particular question about database techniques that you would like to see a video about, just write it down in the comments and I might consider doing a video about that eventually. So thanks and have a nice day.